Good morning, everyone, or good afternoon for people like me, who's in the Far East right now. It's with great pleasure that I would like to introduce Ivan Titov, who is going to talk about interpretability in natural language processing. A very brief intro about Ivan. He's an associate professor at the University of Edinburgh and also University of Amsterdam. And his research is focusing on NLP, natural language understanding, generation, and generally machine learning for NLP. So he's also an action editor at GMLR and Tackle, an editorial board member of GIRE. So without further ado, I would like to ask Ivan to share his screen and tell us about interpretability in NLP.
Hi, everyone. Good morning. Can you hear me well? I think it should be fine.
Yeah, we can hear you well. So maybe you can share your screen.
Mm-hmm. Okay, how do I get rid of this Zoom? Can you see the whole screen, or you can see this Zoom windows as well?
No, this looks good. This looks good.
It's good like that. Oh, it's fine.
Okay. Put up something. Oh my. Somehow I have some panel from Zoom popping up in front of me, so it's not good. Probably can't see it. Okay. All right. Okay. Hi, everyone. Thank you very much, Sophia, for the introduction. So I'm going to talk about work in my group on interpretability in NLP. And this is joint work with my students, Yasmin Bastings, Nicola Decau, and also collaboration with a colleague at the University of Amsterdam, Wilker, Aziz. I suspect many of you are familiar with the state of affairs in NLP in 2020. So carefully designed features, carefully designed independence assumptions for a given task. Tasks have been largely replaced with very flexible, very powerful, very large narrow models. And encoder-decoder picture here symbolizes this type of a model. So we have encoder, which eats, which consumes words in the sentence, produces some kind of representation, which is passed to another component of the model decoder, which generates a prediction. In this case, the translation of the sentence, and it generates it word by word. So these models, this type of models have been extremely successful. We've seen huge improvements on a number of tasks, and we also managed to approach tasks which we thought we won't be able to tackle in the short term at least. But this power comes at the cost of interpretability. And there are a few different definitions, a few different ways of thinking about interpretability, and they are not entirely compatible with each other, and we'll touch on this a little bit in the talk. But what are the general reasons for us to understand the reasoning, so what's going on behind the predictions of the model? For me, as an academic, as a researcher, I'm actually curious, of course, to understand what the models we are designing are actually doing. And I hope that by better understanding these models, better understanding their problems, I will be able to develop, or the community will be able to develop yet better models. From more practical side, revealing machinery behind the predictions should help us to detect some shortcuts which models take. Maybe it's unfair in certain way, or maybe this shortcuts, this reasoning patterns, it relies on not going to generalize to real data it will be applied to. So there are many different reasons to think about interpretability, but I would say that some applications are even impossible without models being interpretable. Interesting. Can switch to the next slide. Okay. So this is a funny example from about 1 year ago when you were asking Google how many legs a horse has, and it was replying 6 legs. And my argument is that we will be tackling more complex and more complex problems, right? And we are bound, and our models are bound to make mistakes. So that's unavoidable. And in this case, Google provides an evidence where it's extracted this information. And this wasn't a web page, wasn't a Wikipedia page about horses. This was a Wikipedia page about logical fallacies. And basically, it was extracted from a joke. And this is what we should be doing. So we should be explaining why we're making mistakes or why we're making correct predictions. And in this way, we will be able to build complex models which can afford making mistakes. So what I'm gonna talk about has a joint general topic which is corresponds to thinking in our group. So in our group, we think that discrete or sparse representations are the way to go if you want to achieve interpretability. On one side, discrete representations are the ones which are easier for humans to communicate. So we are not so good at reading numbers. It's much easier to communicate discrete representations. From another side, we can get some sort of guarantees. It's easier to get some sort of guarantees if we talk about discrete explanations. My talk today will consist of 2 parts. First, I'll talk about building models which can be designed in such a way that they can explain themselves. On another part, we will use similar techniques to extract explanations from models which are trained without interpretability in mind. Why doesn't it react immediately to my... Oh, my keyboard is locked by something, so I have no clue. Now what I'm doing to switch to another slide. Okay. Okay, so this first part is about building interpretable models, and this is mostly work of my student, Bastings. So let's consider a simple setup. So this is a classification problem. So you're given documents and you want to predict for each document some class label, maybe a sentiment, a label. But besides having the prediction, you also want to understand why this prediction has been made. And in this work, we inspired by previous work by Lei et al. From the MIT group. And in this work, they want not only to make a prediction, but they want to do this prediction through the intermediate step. And they call this step rational extraction. So you have some model which takes the text and extracts parts of the text, which only these parts will be used by the classifier. Never happened to me before. Let me just try it again, because it somehow takes it over after a few seconds, and I press the button, it doesn't react. Okay. So then only these extracted parts are used by the classifier, right? So you have in the middle a rational extractor, which predicts the parts, and then you have a classifier which relies on these parts to predict the label. And what you want to do here is not to train intermediate parts to agree with some annotation, but you want to train from this top level label. So you're not going to have annotation at the level of rationals. You want to learn rationals without annotation. So this is some kind of latent variable within the model. So these rationals should be short, okay, because we will be showing them to human. We want to make them read not so much. And then this should be sufficient in the sense that top level classifier should be able to make the prediction. Now, this is very simple math just to establish notation. So we have X is our input. It's passed through the neural network, which is just the classifier parameterized by theta. And on top, we have a softmax. So you have a categorical distribution from which we sample the label Y. So that's a normal setup. So in I need to press 10 times or something to make it work. Okay, let's try more. Okay, so that was original model, just a basic model. And so with the rationals, what you have an extra layer of variable z. So you have a bottom layer neural network, which predicts parameters of a Bernoulli distribution for every token. So for every token, you predict the probability of masking this token. And from this Bernoulli distribution, you sample this mask variable, so 0 and 1. And if it's sampled 1, then this corresponding token is passed through the classifier. If you have a 0, it's masked out, is not available to the classifier. So maybe it's easier to see this in this graphical way. So at bottom you have a model which is our rational extractor. It's parameterized by phi. It produces Bernoulli parameters. You have a layer of binary variable z, and then it's taken by this classifier parameterized by theta. We have this discrete layer in between, so we can't really propagate gradients through this. So if you think of this as some kind of computational graphs, there is no way to propagate gradient. And so as we will see also in some experiments which I'll touch on, it's really hard to make it work. The variance for the gradients is very high. So what do we want? We want to replace this with some kind of relaxation, so which on one side gets us exact zeros. So we still have once this guarantees that we don't pass tokens to the classifier. So we want exact zeros, not just rescaling, and we want the process to be differentiable. So we want basically unbiased gradient estimators. So another part which we want, we mentioned that we want the rationals to be short. So we want to have a way to express preference for the short rationals. And let's just start talking about the second point. So what is the natural way to prioritize, to express preference for short rationals? It's just to count the number of positions at which the mask is non-zero. Right? So if the mask is non-zero, then this token is in some way passed to the classifier. So this L0, this corresponds to L0 regularization. So that's a number of non-zero components. So the reason why you don't hear that much about L0, unlike like L2, L1 in machine learning, that is not differentiable. So it's pretty hard to use. But recently, there was a proposal in the context of pruning neural networks is to replace these binary variables with relaxations. And this is work by Chris Luizes, and I'll explain briefly this technique, which we use in our case to prune the input. And so what they used is they call hard concrete distribution. It's actually not very complicated construction, but I have quite short of time, so can't really walk you in detail through this. But this is a family of distributions which has a which is discrete at 0. So it's defined on a closed interval from 0 to 1. It's discrete at 0, discrete at 1, and continuous in between. So it's mixed, continuous, discrete. And here you can see that by selecting different parameters of this distribution, you can change the shape, and the probability mass, for example, corresponding to generating exact zeros changes. So in this last position, you mostly sample zeros. So you mostly mask the corresponding position. So what we get here? We get exact zeros. The process is differentiable, so we just can plug it in a computational graph and use automatic differentiation, so it's pretty straightforward. We can also compute the L0 penalty, so it's available in closed form, because CDF of the distribution is available, and also it's differentiable. So what we do conceptually is very simple. So we replaced this neural network which predicted Bernoulli parameters. Now it's predicting parameters of this hard concrete distribution. And now we sample Z, which is not exactly binary, but it also has this continuous, potentially continuous values in between. But we will be regularizing it towards 0, so towards masking the items. So now I'll present a couple of experiments. So this experiment on a classification task. So interpretability, this sparsity will come at a cost. So there will be a trade-off between accuracy and interpretability, between the sparsity. So horizontal black line is a performance of the classifier which has access to the full input. And horizontal axis shows the proportion of text given to this onto our model and this Bernoulli baseline, which was trained with reinforce. So you want to be as close to the horizontal line as possible, right? And so what we see is that by selecting only a quarter of text, we essentially don't lose performance almost at all. As we select less, performance drops. But we also much higher than the model which was trained with reinforce. So then another question is, how do the rationals look like? And for this, there are some data sets where humans annotated what they think should be predictive of the label. So we can compare rationals extracted by our systems or also baselines with rationals provided by humans. And we can in general see that agreements with humans is pretty high for our method and also for Bernoulli reinforce admittedly, but our method is much more accurate. Even so, this accuracy, of course, is not really necessarily what you want. It's nice to see that the model agrees with the humans, but humans may be also annotating not what the model should be relying on, right? So that's just to give us some intuition about the model behavior. Okay, so that was about building interpretable models. So we can see that we can construct models which show which parts of the input they rely on. And we can do this in a relatively straightforward way while preserving differentiability. But generally, there is a trade-off between accuracy and sparsity. It's not always has to be the case. So we also looked into using similar techniques to enforce sparsity in encoder in the case of speech-to-text translation. And in that setup, it was actually useful not only from interpretability or also efficiency perspective, but also from performance perspective. So it was useful to prune the input space. So this work, which is not yet published. Now let's think how we can extract representations from the models which have already been trained, right? So this previous technique comes with some overhead, implementation overhead, efficiency, maybe overhead in certain cases. So now let's think we have a model which is trained to solve a general task, but we want to extract the explanations. And let's get back to the question answering task. So we saw previously questions about the horses. Now this is the squad data set. So we have a question where I did the Broncos practice for the Super Bowl. Oops, there is a typo here. And there is a passage where we should need to rely on. So this is a very simple case, and it correctly identifies the answer Stanford University as a place where Broncos practice. So what we want to understand, how the model reasoned here. And this is a very large model. So we use a 24-layer model, which relied on BERT. So this is contextualized embeddings. You probably aware of this type of these representations. So the pre-trained model. And it's rather hard to understand how it's arriving to the decisions. So one of the techniques which is generally regarded as the most faithful, and faithfulness is important here because we don't want to get just explanation which is plausible to us as humans. We actually want to understand how the model behaves, right? So if model makes some stupid shortcuts, we want to see that. So this technique is subset erasure. And subset erasure is selecting a minimal subset of tokens, which when passed through the model, yields the same prediction as the original sequence. Besides computational problems of this, it's extremely expensive, so we have to use approximations. It's also over-aggressive. And it's over-aggressive because what we call a hindsight bias. So in this case, it will select the only subset is the answer. So it basically will mask everything except for the answer. And the model predicts this as an answer to the question. So does it tell us something about the model? Yeah, I guess it does tell us about some problems, but it doesn't really tell us about reasoning in normal case. And to see this, let's have a look in a very simple toy example. So in this case, you're given a sequence of digits. So say 883139, and also a pair of digits, a query, and you ask to decide whether the first or the second digit in this query is more frequent. So the query here was 1 and 8, and the answer is 8 because 8 appears twice in the input sequence. So it's a very simple task. So two-layer neural network predicts it perfectly. So it has almost 100% accuracy on the test set. So now when we apply subset erasure to this model, what we will see that it will select a single 8-digit as a subset. So it's basically just reduce the whole example to the single digit. And it's not surprising because, of course, on this single digit, on this singleton, the answer is the same. But it doesn't really tell us what the model relies on, because we know that it's performing counting. So it has accuracy of 100. So we actually know that it must be reading the whole sequence and doing processing. So instead, we, inspired by this, we do the following. So we use a subset of layers, so say up to layer L, and trying to predict from these layers using the hard concrete masks, hard concrete case, which tokens should be masked, which tokens should be kept. And in this way, we are trying to see what the model actually knows at layer L. Whether it knows that these inputs are still should be considered, or it already knows that it discards the corresponding input. So in a way, maybe you've seen an NLP, there's been a lot of interest recently in probing representation, in trying to see if representation encodes certain linguistic property. Here we are not probing for linguistic property like syntax or semantic representation. We're probing the model if it knows that this, for example, candidate answer it can be an answer, and we can see what it does. So when we apply for the toy task, when we apply, we're making the model to predict it from the bottom layer. Model has no idea because it hasn't integrated yet as a query information. So it cannot mask anything. So it keeps all the tokens in the sequence. So if you apply this to a hidden layer now instead of a bottom layer, it already knows about the query, but it hasn't performed counting yet. So that's why it keeps all the aids and in the. So this was, of course, an artificial example. So now the question is, how does it look like on a question answering tasks? And so what we see here on the right is a diagram corresponding to the question and the passage you saw before. So on the horizontal axis, you see layers of the neural network. And on vertical, you see words in the question and in the passage. So the yellow parts are the tokens which are kept, and the purple ones which are dropped. So you can see how
Sorry to interrupt, Ivan, but you're out of time. Perhaps you can have 1 minute to wrap up.
Yeah, I think I just need half a minute. I'm sorry, some technical problems.
Yeah. Okay,
yeah. Okay. So so what we can see is, for example, that the answer and the key information survive until the very end, and this is not surprising. So it can't drop the corresponding tokens. So other crucial information, for example, the candidate answers. So it could have answered San Jose Marriott. So it was a possible answer for the location for training. It survived for quite long as well. But we see that after 20 layers, the model essentially converges to the answer. It already decides what the answer should be from this diagram. And the interesting thing that words like stay, it can drop very early on, so it actually doesn't need to observe this word. And I think we have some explanations if I have time for questions. So this essentially concludes my talk. So we talked about ways how to build models which can explain themselves. We also showed that similar techniques, again, this hard concrete case, can be used to review the decision flow within deep neural networks. We can also apply similar ideas to models which have been usually considered very hard to explain, like graph neural networks. So thank you very much.
Thank you very much, Ivan.